Good morning. Today we are going to go over pH calculations, or that is calculations from pH. But first, I'd like to review what we did a week ago. Lots happened in that break, and what we're doing today is going to require that foundation. So let's just do a little review and then we'll jump right in. So this is from your acids and bases worksheet. The first thing we did was to identify what things were acids and what things were bases. So just to kind of go along here, help me out here. NH3 is a what? It's a base. It's one of our two bases that doesn't have a negative charge, right? That and water. What about this guy, HPO4 2 minus? This is both. Amphoteric, because it has the negative charge, so it can attract a hydrogen, but it also has a hydrogen it could give away, and it's that phosphate polyatomic ion that's there. Okay, what about HClO4? Strong acid. This is one of the ones that we have to memorize, right? It's the strong acids. What about calcium hydroxide? Base. Yeah, you have to recognize that hydroxide there can act as a base. Great. What about NH4 plus? Acid. Excellent. It's got the hydrogen to donate. Certainly it's not going to attract a H plus because the positives won't attract a positive. Good. Okay, so let's do section 2 here. Super quick review. Okay. We need to figure out what's the acid, what's the base on the reactant side, and what's the conjugate acid, what's the conjugate base on the right-hand side. So the Na2CO3 plus HCl, in this case, the Na2CO3 is the base, good, and the HCl is the acid, okay? And you can see that because this has no hydrogen to donate, so it can't be the acid, right? And HCl is one of those acids, one of the like 6 or 7 that you are asked to memorize, so you should know that. And then when you go to make your product, you'll see also that the CO3 picked up a hydrogen and accepted one, which is our definition of a base. That makes this the conjugate acid. Because if I was going backwards, that hydrogen would be donated to leave me with the CO3. All right, and then this is the conjugate base. Perfect. All right, one more. You guys are quick. H3PO4, that's the acid in this case. That's right, there's no negative charge or anything. It's just a bunch of hydrogens. And this is, of course, one of the two bases that we memorized that doesn't have a negative charge. So acid plus a base. And you can see here that the H3PO4 has indeed lost a hydrogen, so that kind of confirms it, which means going backwards, it would pick it up. That makes it the conjugate base. Good. And now here, this is the conjugate acid. All right. So far, so good. Okay. So, moving on, and we're only going to do one of these. Okay, this section 3 comes straight out of your chapter 9 material, and I think we did parts 1 and 2 last time, so we'll do parts 3. And it's really easy to get lost. I'm glad you said that, Zach, because you are not the only one getting lost here, and it's really easy to get lost. So just as a reminder, I'm going to strongly recommend that we're going to use this conversions roadmap, and we're going to go off-roading, right, and say this is applicable for solutions, and of course acid-base solutions are included, right? But if you have moles, you can find the concentration of the base, the concentration of the acid. That brackets means concentration. Of course, you need volume for that because concentration is that we care about, at least the concentration units we're using are moles per liter. So you need the volume to get to liters. So using just this little set of off-roading, then we can identify where we're going from and where we're going to. So of the base, they gave us 0.750 liters. They want to know the concentration, and they gave me milligrams of the acid. So if we said A was acid, 59 milligrams of the acid is going to go down here. And we have 0.750 liters of the base. And this is our target right here, the concentration of the base. Does that make sense? Do you see that? All right, so according to this, I do have to go from milligrams to grams, and then from grams to moles using the molar mass of HCl, and then the moles of A to moles of B, and then the moles of B to concentration of B. And specifically, actually, you can't answer this without a reaction specifically. And the reaction that they're talking about was in part 2, but I cut it off, so I better bring this over here now that we're curious. This was part 3. We just didn't do it. But this problem is talking about this equation. There we go. There's a missing piece. Very important. Yes. Thank you, Erica, for catching me. That should be HBr and not HCl. Here we go. Okay, you ready to do this? All right, so 59.0 milligrams HBr. Good. And next, we need to go to grams, right? So what's that going to be? Oh, excellent. But you're a step ahead of me, because here I've got milligrams instead of grams. So we have to take that extra step and say that, 1 gram of HBr has 1,000 milligrams. Really, that's true of anything, but since we're working with HBr, we should include those identity units. Good. Now we've got grams on top, and as you guys noted, the molar mass of HBr is 80.908. The units for that is grams per mole. And where am I going to put the grams? Yeah, Zach, we had to switch to grams so we could use the molar mass from the periodic table, because that is in units of grams per mole. Right, grams go at the bottom, so they'll cancel. Perfect. So grams per mole becomes moles per 80.908 grams. No biggie. We put those units where we want them. That is the name of the game with dimensional analysis. And by the way, milligrams of HBr cancel. Grams of HBr cancel. Okay. Sarah notes that our coefficients here are 1 to 1. It didn't look like we went out of our way to balance it, but if you glance at it, you'll see it is already balanced. That's obviously not a guarantee. My identity units, okay. And my measurement units, okay. Excellent. So now we have moles of NaOH. We've got to here, moles of B. They want concentration, and they gave me volume. So what am I going to do with that volume to get concentration out of this? Divide. Perfect. So we don't at this point want to cancel out moles, because we need moles divided by liters for that last bit. And then we plug it in, and we get 59 divided by 1,000 divided by 80.908 divided by 0.750, And Sarah and I both got the same answer. We have 9.72 times 10 to the negative fourth molarity. All right, does that make sense? Excellent. All right, the next thing that we did last Tuesday is we said, hey, this is great, but we actually want to use the pH scale because that's the way that everybody represents how acidic or how basic something is. And I noted on your exam support materials, in fact, I'll just copy this right on over. Got this brick of equations that I give you. So if you want to know the pH and I gave you the H plus, well, we just plug that in, right? We're going to say, all right, well, I need the minus log of 0.10. And depending on your calculator, you're going to put it in a different way. In this case, I'm going to put in the 0.1 and then the log and then the negative sign, and I see I have a pH of 1. If it's the hydroxide, I can use that to find the pOH directly, and then I can plug it into this equation to find the pH. So I can take the minus log of 0.12, log minus, okay, now subtract that from 14, so minus plus 14, and that gives me a pH of 13.08. You guys remember how to do those? And then we just said, oh, hey, look, fancy. If this is my base, this is my acid, that concentration plugs right into this equation. So we're still off-roading, but now we're going to use an equation instead of our dimensional analysis and say, if indeed this is the H plus, then I can find the pH directly from that. Or if that's the OH minus, I can find the pOH directly from that. And of course, if I wanted the pH, then I'm going to take another step here to find the pH. Technically, I could do that down here, although it seems a little bit silly. Only because nobody ever uses the pOH scale. But as proof of concept, you guys should know that, okay? So here we're just using that pH plus pOH is equal to 14 equation. Here we're saying pH equals minus log of the H plus. It's the equation we're using. Make it fit. There we go. pOH equals minus log of the OH minus. Okay. And so the rest of these here, I just gave you the concentration, so I plugged it in, but this was an exercise in finding using moles and milliliters to find concentration and then plugging it in, or using grams and liters to find moles and then finding concentration and then plugging it in. I feel like you guys can do that pretty well. And the very last thing that we did was to put it all together and to say, all right, well, go calculate pH of this thing. Yeah, so you'll see how it kind of builds, right? As Sarah notes, you have to check to see if what you're looking at is an acid or a base, right? Because if it's a base, you do have to take this extra step, right? But if it's an acid, you don't. And you just gotta kind of check that, check yourself and make sure that if you're solving for the pH of an acid, it should be between 1 and 7. And if you're solving for the pH of a base, it should be between 7 and 14. Okay, so in this case, and I'm kind of feeling like I shouldn't have marked up this one so much, so I'm just gonna copy this down here and then use it anew. Let's clear out all my work. Okay, and then we were also just gonna be clear that this is my acid and this is my base, right? And so that makes this the OH minus and this the H plus. Let's be specific about that. Because it's my base. This is because it's my acid. Okay. All right. Now I'm going to copy and paste this because I'm going to use it again later. Okay, so for this particular problem, let's see, they want the pH of the acid solution. So this is my target here, the pH of the acid solution. And they gave me that it's 590 mils, so that's going to go here. And they give me that it reacts with, here's moles of my base right here, 0.0372 moles of my base. So hopefully you can see I'm going to go from moles of base to moles of my acid, use the volume to go to concentration of my acid, and then I'm going to use this formula to get to pH, right? Walk me through this. I can see I'm starting here. What should I do next? All right, you see my mole to mole ratio, which is 1 to 1, it looks like. We will see some examples later today that are not 1 to 1, I promise. Okay, so my moles of carbonate cancel. And that gets me to moles of acid. Good, what do I do next? Oh, good. And I don't even need to do that on my dimensional analysis. I'm going to convert that to 0.590 liters, right? I'm just going to plug that in here. Okay, now what? I'm going to stop. I'm going to get off my dimensional analysis chain here because now I need to jump into a formula. I'm just going to kind of move fluidly between our formulas and our dimensional analysis. Okay, gives me 0.631 moles per liter. Okay. Oh wait, there's a 0 there, isn't there? Yeah, there's a 0. Okay. Excellent. Now what do I do? Take the minus log of that. The minus sign. Okay. All right. Log of that, negative of that, 1.2. And since this is the acid and I wanted the pH, then I'm done. Right? Easy as pie. Well, I don't know if it's easy as pie. Pie is pretty easy to eat. Maybe easy as making pie if you've done it lots of times. Okay. All right, what we're doing today then, so that was a little bit of a review, but I wanted to make sure that we felt a little bit polished up on this. So today we are going to go backwards. So the new thing that we're doing today is using, where are they? Using these equations. If I give you the pH, how do you find the hydrogen concentration or the hydroxide concentration? And it's a different equation. I mean, it's the same equation, but it looks very much like a different equation. And the reason that it looks different is because just properties of logs, right? So 10 raised to the is the opposite of a log based 10. So if you wanted to take the inverse of a log, so you could take this equation and solve for the h plus, this is what you would do. You'd take 10 raised to both sides. Actually, you'd move the negative sign over, you'd take 10 raised to both sides, and then you'd be able to solve for the h plus if you had the pH. But because it's probably been a long time since you guys memorized your properties of logs, and that's not really the most important thing that we're doing here. I'm just giving you these equations, and I'm happy to have you just memorize them and be like, oh yes, when we go this direction, we use this other equation, okay? So that's what we're gonna do. Just going backwards, and I give you the equation. So hopefully it's not too tedious. So you're gonna look on your calculator. Now this is a little bit tricky. It's different than what we've done before with the exponent, right? Because previously if we did like 1 times 10 to the negative 5th or 1 times 10 to the negative 6th, that was a whole number. And generally speaking, I don't know if this one is gonna do it. No, it's not gonna, hang on a second. Generally speaking, your calculator, this is not gonna, yeah, it won't even let me put a decimal sign in that exponent. So the key that you've been using, if you've been using the double E key or the EXP key, or even the 10 raised to the key, it probably won't work to help you solve this problem. So depending on your calculator, what you're probably looking for is a key that has an x to the y. That would work. You could say 10 is x, and then your y is your pH or your POH, or you could use 10 to the x. That will let it be anything. Or you might use a little caret button. This one doesn't have it, but the little caret might work, okay? Let's practice just a few of these. And right now I'm in your second worksheet from your acids and bases. And just gonna copy this all in here. It's not hard, it's just different. Haven't done this before yet. Okay, so what we need to find out the H plus is we need to take 10 to the negative 4.5. All right, so on my calculator, I'm gonna say 4.5 negative, I'm gonna take 10, I'm gonna say that's X, and I'm gonna hit 10 to the X. And that's the number. Again, every calculator does it differently. I sincerely hope you have yours right now and that you're plugging this in so you can figure out what buttons your calculator wants you to push in order to solve this problem. Does the caret work for you, Erica? Good, yeah. And it's very, very clear. Okay, so that gives me 3.16 times 10 to the negative 5th for my H plus. Perfect. Oh yes, and 10, Sarah says 10 to the X works on hers. Okay, good. All right, so that's how we found the H plus, but they want us to find the OH minus 2 for, this looks like an acid because it's got a pH of 4.5. How am I gonna find the OH minus concentration of this guy? Sarah's exactly right. Given these equations that I have, I can just take the pH and plug it in here to find the pOH. So 14 minus 4.5 gives me the pOH. Okay, and then I take 10 to the negative pOH, that is 10 to the negative 9.5, and that should give me my hydroxide concentration. So 10 to the negative 9.5 gives me 3.16 times 10 to the negative 10. Does that make sense to you guys? All right, so this is not particularly challenging. These are all exactly the same. Let's do just one more, and then we can, I think, move on from this if everybody feels good about it. Let's do this one, pH of 10.1, because looks like it's in the basic range, right? we can still just directly 10 to the negative 10.1 and 10 raised to that gives me 7.94 times 10 to the negative 11. So I'm sorry, Erica. That must have been on the homework. We just didn't get quite that far on Tuesday. So that makes sense. I can see why that'd be confusing. All right, so if we subtract 10.1, this gives me my POH, so 10 to the negative 3.9. There we go, 1.25 times 10 to the negative 4. There we go. Now, your book and your homework also probably has you use that equation. We did talk about this last Tuesday. The H plus multiplied by the OH minus is equal to 1 times 10 raised to the negative 14. And they might say, look, if you find the H plus, you could just plug it in here to find it. But I find it easier to just use the whole numbers and not deal with a whole bunch of exponents, which is why I don't give you this equation. Again, this equation is the same as this equation according to the property of sublogs. Yeah, so this, Erica, you're right. What we're doing here is we're finding the concentration, which is in units of molarity, moles per liter, of our acid and base solutions. So the concentration of my acid in this solution with a pH of 4.5, the concentration of H plus is 3.16 times 10 to the negative 5th molar H plus. And this is 3.16 times 10 to the negative 10th molar hydroxide. I should probably include those identity units. Should definitely include those identity units. What with spending all semester harping on you guys about don't forget your units. I really ought to, right? Okay, so this next step in your worksheet is just taking this one step further. That is, if I give you grams and liters and pH, then, or sorry, if I give you liters and pH, can you go back to grams, for instance? Or if I give you liters and pH, can we go back to moles and so on and so forth? Now, this problem, these problems, we could use our conversions roadmap for them, although they're not reactions. Just gonna bring this up here. They're just going back and forth either along the base trail or along the acid trail. And on the next section, we'll kind of put it together, right? The new thing that we're doing here again is we can go back this direction, and we can go back this direction. Note how I have two different arrows here instead of a double-headed arrow. The double-headed arrow says, hey, you can use the volume, moles, like all of these are interchangeable using your dimensional analysis. The double-headed arrow says this equation can be used to go either direction. Here I have two arrows, and that says I'm going to use this equation to go this direction and another equation to go the other direction. That's kind of how I have that set up there. Okay, and again, we're going to say my H plus is equals to 10 raised to the negative pH. And here it is, my hydroxide is equal to 10 raised to the, negative POH. Right, so just a different equation to go this direction. All right, so for this one, they want to know grams of acid, they give the volume of the solution, and they give the pH. So this is all the same solution. They gave me the pH of my acid, They gave me the volume of my acid. Let's see, I can put these in here. pH was 1.85. My volume was 0.580 liters. And they want the grams of that acid. So they want me to come down here, right? So even though I'm not doing a reaction, I can still use this roadmap. It can still be really helpful. And Sarah is on top of it. She appears to have solved this problem already because she's amazing. So we're going to go backwards from here. We're going to take 10 to the negative 1.85. Okay. All right. 10 raised to the negative 1.85. Let's see if we get the same answer as her. 1.85. Negative 10 raised to that. I get an H plus concentration of 0.0141 moles per liter. That's capital M for molarity, but that's not helpful. So we're gonna just convert that to moles per 1 liter of that solution. Okay, we did that equation. And now we're just gonna fluidly move right into dimensional analysis and say I was given 0.580 liters of solution. I'm gonna stick that right there. Okay. And then if I do that, my liters of HCl solution cancel, and I'm left with moles. Just like I should have. I went from concentration, I used the liters, I found moles. To get to grams, I need the molar mass. And I know that Cl is 35.45 and H is 1.008. So I get a molar mass of 36.458 grams per mole. I'm going to put that on top. If I do that, my moles of HCl cancel. And no, there's nothing on the bottom here, right? I'm putting my units where I want them to get what I need. Okay, so 0.0141 times 0.580 times 36.45, and I get 0.299 grams. Yeah, 0.299 grams of HCl. Does that make sense to you guys? So much of this is not new, right? This piece is the only new piece that we're just adding in, right? This going backwards from the pH, and then the rest of this is old hat. Okay. So same thing here, but now I'm looking at a base, and I'm going to say, all right, my base has a pH of 10.4. So I'm all the way out here. Do this in a different color. We'll make it green. Okay, so my base has a pH of 10.4 and a volume of 1.52 liters. And they want to know the number of moles. Do we have enough information to solve this problem? Feels like kind of sparse. Let's see. I can go from the pH to the pOH using that equation. And I have to do that because it's a base, right? So I had to know to use this line and not this one. Okay, and then I can find 10 to the negative pOH gives me my OH minus concentration, which is in moles per liter. And then if I use the liters, I can get back to moles. I can do that. We can do that. Okay, so step one, going from the pH to the pOH, we're going to say my pH plus, my pOH plus my pH is 10.4 is 14. Okay, so 14 minus 10.4 is going to give me my pOH, which is 3.6. I shouldn't have needed a calculator for that, but I did it anyways. All right. And then from here, we're going to say 10 raised to the negative 3.6. That's going to give me my OH minus concentration, right? We're going back this direction. which is in moles per liter. So 3.6 negative 10 raised to that. It gives me 2.51 times 10 to the minus 4. And the units here is molarity, which is moles per liter. And specifically, since I'm in my base here, it's moles of my hydroxide per liter of that hydroxide solution, right? So now, if I've got liters, just plug that on in, 1.52 liters. My liters cancel. And we get 3.82 times 10 to the negative 4th moles of hydroxide. Now technically it's moles of hydroxide because here we just went from the pH to the POH to the hydroxide concentration. But because I'm sodium hydroxide disassociates completely. 1 mole of sodium hydroxide is going to give me 1 mole of hydroxide. Then I can basically say that is the same thing as 3.82 times 10 raised to the negative 4th moles of NaOH, right? It's the same thing. 1 mole of sodium hydroxide makes 1 mole of hydroxide. And if it makes me feel better, I can always just add that into my line here, right? I can do that. How'd you guys feel about these guys? Erica, that is such a good question. Erica says, now wait, what if it doesn't disassociate completely? And the answer is, then we don't do this equation. We use something different, which we just haven't got to today. But we can only use this for this kind of assumption, this one-to-one for strong acids and strong bases. Excellent question. Okay, shall we take it a step further? Uh-oh, I just wrote all over all my roadmap. I need it. Okay, let's take it a step further, shall we? So this last section, we just said, look, if I know stuff about acids, we can go back and forth here. This next section says, let's do a reaction with an acid and a base. And we can go like all the way from here all the way up to here. We're gonna go off-roading here and do a little bit more than we have already done. Whoops. So this is section 3 from your worksheet here. I've got space over here. Let's just do, I'm gonna do just the bottom 2. You guys can do the top one. All right, so I'm using this equation for this reaction, and this is a different one, okay? So this one I give you the equation, the other one I don't. So to solve these problems, our roadmap has gotten bigger. It needs its own space up top here. Okay, calculate the pH of a 550 milliliter HI solution, which fully neutralizes a 1.25 liter potassium hydroxide solution with a pH of 9.8. So first things first, Erica says, check, is it balanced? Is this reaction balanced? Okay, what does it need? Oh, it is balanced, right? 1H plus 1OH, that's how I get my H2O, it's HOH, right? And then 1I and 1K gives me Ki, that's good. It's balanced. But it's always a good idea to check, because I promised you that it would not always be a 1-to-1 ratio. And I promised you that you would also get a chance to practice one of those today. All right, the next thing I want you to do is define what is your acid and what is your base, because now it's important to know which part goes where. So my HI, is that my acid or my base? That's my acid. Good. And my KOH, is that my acid or my base? That's my base. Good. All right. So I have my acid here and my base here. And they want to know the pH of the HI. They want to know the pH of the acid. So we are going to make a copy of this and use it elsewhere. Stick it over there. Okay. And then I can write all over this and not feel bad. They want the pH of the acid. This is my target. Dun, dun, dun. pH of the acid. All right, and what did they give me? They gave me the volume of the acid, 550 milliliters of HI solution. They gave me the volume of the base, 1.25 liters base solution. And they gave me the pH of the base. That comes 9.8, all right? See why it was really important for me to identify what's the acid and the base, because I'm looking for a pH and I was given a pH, and there's 2 pHs on here, and it's important to know which one you have and which one you're looking for, okay? Sarah says, I'm just gonna not waste my time. I'm just gonna move that over and say that's a 0.550 liter solution. I think that that's a great idea. Okay. So I've got 3 different pieces of information, and they're kind of scattered along this route. But remember, we're going to start at the furthermost position, and we are going to move in or converge onto our target. So this is the furthest most position, right? So we're going to go from here all the way this direction, wrapping down around all the way this direction, and we're going to get to our target. Does that make sense? Hypothetically. Sarah's done our first step. She says, look, I'm going to use this. My pH is 9.8, so 14 minus 9.8 should give me my POH. Go. Which is 4.2. That's right. Good. Our next step is from here, we want to go this direction. I have to take 10 raised to the negative POH to give me my OH minus concentration. So 10 raised to the negative 4.2 is equal to, what do we get? 4.2 negative 10 raised to that, 6.31 times 10 to the negative fifth. Right? Everybody agree with that? This is my OH minus concentration. Okay, oh, I don't know what I did there. I did something I didn't mean to. Okay, and of course this is in moles per liter. Right now I'm right here. And now I'm gonna jump on dimensional analysis, right? So let's 6.31 times 10 to the negative fifth. Moles per liter. Good. All right. What next? Where am I? I am, found the POH, got the OH minus, I am here. What shall I do next? Divide by the volume, 1.25 liters, okay? Right there? All right, and my liters, let's see, here we go. Now what do I do next? Oh, Erica caught herself. I'm just waiting for somebody to say, wait, stop. It was on top, right? How did you know that you did it wrong? How did you know it needed to be moved? Yes, because it doesn't cancel. Yes, perfect. That's exactly. And I'm glad I left it there because I knew it would show you if you were looking for it. And I'm glad that you looked for it. Perfect. Totally fine. All right, so now we've got moles of hydroxide, which is the base, which is just where we wanted to be. And so next we're going to, I know it's 1-to-1, but we always have to put it in here because otherwise our units don't cancel. All right, so 1 mole of, oops. It's 1 mole of KOH to 1 mole of H plus, or 1 mole of OH minus to 1 mole of H plus, right? We're gonna say, if we 1 mole of KOH to 1 mole of OH minus, right? If we wanted to add in that extra one, but I have no problem just saying, look, I've got 1 mole of H plus here reacting with every 1 mole of OH minus. I am kind of skipping that extra step, right? And I need to be explicit about that I can see that 1 mole of HI is equal to 1 mole of H plus ions, and that 1 mole of KOH is equal to 1 mole of OH minus ions in solution, right? This is kind of the unspoken thing that's happening here. All right. If I do that, my moles of OH cancel, and I've got my moles of my acid right here. And to get concentration, I need moles per liter. So I'm going to divide by liters, so I get liters on the bottom, just like Sarah said. 0.550 liters of that H plus solution. That gives me my H plus concentration here. Good. Which is, let's see, so 6.31 times 10 to the negative fifth. Multiply that by 1.25. Divide that by 0.550. And I get 1.43 times 10 to the minus fourth. Is that what you guys got? All right, and the units here, that's moles per liter. So this is my molarity of my H plus. And now, if I want to get to the pH, I'm going to take the minus log of that. So log of that, minus of that, and I get a pH of 3.84, which is what Sarah got. So minus log 1.43 times 10 to the negative 4 equals 3.84, which is my pH. And that's my answer. What do you guys think? Nothing new or different. We're just putting everything together. And I hope that when you look at this, you go, I'm so smart. Look at what I did. It's amazing. That was a huge problem. I did algebra, I did dimensional analysis, I did more algebra, and I got the right answer. All right, let's do it one more time. One last one, and then we can take a break before we talk about what happens if it's not a strong acid or a strong base. Okay, so what volume of HNO3 solution at pH 1.07 is required to titrate 15 milliliters of 0.012 molar barium hydroxide solution? Now, there's a word here that I'd like to draw your attention to. If you use the word titrate or you see the word neutralize or react with, all of these mean the same thing. So titrate is the same as neutralize perfectly, is the same as react with, and so on and so forth. Titrate is kind of a fancy word to say, like, look, I'm using something that I know. Here it's a barium hydroxide solution of this concentration to determine something that I don't, right? And what I'm going to do is just react them together until they have reacted perfectly, right? And then I can calculate based on how much of this I know will react with that. I can calculate what I had over here, okay? So don't be confused by this word. It's just kind of a fancy word for, hey, I'm reacting it together. Okay, so that is just that one word there. All right, so Sarah says, wait a second, don't we need the equation? And the answer is, of course we do. And did I give it to you? Of course I didn't, because I'm rude like that. And at this point in acids and bases, you should be able to come up with that equation. And I'm going to make you do it. Haha. I mean, I'll help you, but all right. So Sarah says, look, if I put HNO3 together with barium hydroxide, then the barium is going to go with the nitrate and the H is going to go with the OH. Well, I knew the H was going to go with the OH, right? So that's just water. But important to notice, oh, whoops, missed a piece here. Important to note that the barium being in group 2, it has a charge of +2 and the nitrate's -1. So when you do this, it's very important to take that into account when you make your product. You're going to need 2 nitrates. If you just put BaNO3, you'll find you can't balance the equation. It's impossible. So if you find it's impossible to balance the equation, check your species. Make sure that you put your products together correctly. When you balance this, you find that you're going to need 2 nitrates, right? Because you're going to have 2 of that barium. And then the 2 H's plus the 2 OH's will give you 2 waters. Sarah got this. She's on it. Okay. So this is the one I promised you I'd give you an example where it's not a 1-to-1 ratio. It's a 1-to-2 ratio. Okay, that's important. All right. But now we have our equation and it's balanced. And we would like to solve this problem. But it will help if we have my roadmap. So I did put this over here so that I would have one that wasn't all marked up. Okay, we're going to use our roadmap. And what's my acid? What's my base? Barium hydroxide, that's my base, yeah. Which means that my HNO3 is my acid, good, which is a strong acid. All right, so they want to know the volume of the acid. So this is my target here. Ooh, fancy. And they gave me the pH of 1.07. Okay, so they gave me this piece. And they gave me the volume of 15 milliliters, and they gave me the concentration, not of the hydroxide, but they gave me the concentration of the barium hydroxide, right? So here, I'm gonna move this out because I don't need these pieces anyways. And I'm gonna say concentration of my BaOH2 solution was given to be 0.012 molar. Okay, do you see what I did there? Now, I could have just left this here and said, okay, I'm going to do this separate thing. Hang on a second. In fact, I'll go back. I have an extra step to take over here because I need to go from my concentration of my barium hydroxide to my concentration of my hydroxide. That's another way of doing it. Maybe I'll do it that way instead. Either way, you should recognize that here, I didn't just give you like the pH and the pOH of my acid and my base. I specifically gave you, what's your units, the barium hydroxide right there. Okay, here's all my pieces. Sarah says, I'm not gonna bother with this like milliliter garbage. I'm just gonna convert that straight to liters and have it done with. I think that's a great idea. Divide that by 1,000 and you have the liters. Okay. One other piece that I'm noticing here is that my volume's in the middle, right? Usually, as we did here, like your volume's at the end. So how do you solve a problem when what you're looking for is in the middle of the roadmap? Yeah, we're gonna converge on it. So we can come from this direction and stop at moles, and come from this direction and stop at molarity. Once I have moles per liter and I have moles, then I can use that, put those together to find volume, right? Okay, all right. We can do this. Where shall we start? All right, Sarah wants to start on this step. I'm just gonna go backwards. This is my pH, so 10 to the negative 1.07. Should give me my H plus concentration. And that is 0.085. I believe you, that sounds about right. Yep, sure enough. Okay, and that's moles per liter, right? Moles per liter. Okay. Now what? Okay, 1 divided by, you want me to flip this upside down? One liter, this is my HNO3 solution. And 0.085 moles HNO3. I'm very proud of you for flipping it upside down and starting with what we want at the end. I know that I call that going backwards, right? That's not the way you usually roll, Sarah. I'm impressed. We want liters at the end, so she's just gonna set that up right there to put the liters there. Now what? So this went right here. And this is what we're looking for, right? The volume of the HNO3 solution. Okay. All right, so now that's the piece that's gonna go here. Now we're gonna start from this direction, all right? I'm gonna do this in brown. Okay, so we have 0.012 molar, which is moles of barium hydroxide. Every 1 liter of that barium hydroxide solution. Okay. Good. You can either say I've got 2 hydroxides for every barium hydroxide, or you could say I'm going to have 2 HNO3s that are going to react with every 1 barium hydroxide. Doesn't really matter, whichever one you say. Sarah says I've got 2 hydroxides. Sorry, 2 moles OH minus, and every 1 mole BaOH2. That's just fine. Excellent. Now what? Now I still have, and I've got my concentration, my OH concentration, instead of my barium hydroxide concentration. right? Divide by 0.015 liters of my hydroxide solution. Oh, Sarah says no. No what? What'd I do? Oh, multiply. How do you know? To cancel. Good, I have trained you well. Your liters of solution cancel. Good, and we got the 1:2 ratio right here. Like I said, you can either, if we go this direction, then that takes it into account. Otherwise, we could do it here, but you wouldn't want to do it twice, right? Now we've got just the moles of hydroxide. How many moles of hydroxide are going to react with my HNO3 solution? Because we want 1 mole of hydroxide on the bottom, right? Reacts with 1 mole of my H plus or HNO3 solution. So my moles cancel, moles of hydroxide, and I have my moles of H plus. Sweet, and now I can like plug this right into that green equation. Or you know what's easier? I'm just gonna plug the green equation in here. That's a little bit easier. One liter of that HNO3 solution has got 0.085 moles of the HNO3 or the H plus in it. Okay, so when I do this, the moles of H plus, which is the same as moles of HNO3, those cancel. Everything cancels except for the liters of my HNO3, dun, 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 dun. And we can say 0.012 times 2 times 0.015, divided by 0.085, and I get 4.2 milliliters. Sarah, you got something different. Or 0.042 liters. Okay, now Eric is like, wait a minute, why did I put 1 to 1 here and not 2 to 1, right? Because there should be like a 2 to 1. The answer is I actually took this into account when I did it here, right? But I could do it the other way, right? I could say, look, I've got, and we'll do it here, 0.012 moles BaOH2 in every 1 liter barium hydroxide solution. And then I could say, look, I've got I'm going to skip this step, right? 0.015 liters of my barium hydroxide solution. Now, if I'm at moles of my base and I'm going to moles of my acid, now I can use that ratio. This is totally fine. You'll get the same exact answer. And here's where you say, all right, I have 2 moles of HNO3 that will react with every 1 mole of barium hydroxide. So now my moles of barium hydroxide cancel. And once you have your 2 moles of HNO3, you can plug this guy in here, right? And say, all right, well, every 1 liter of my HNO3 solution has 0.085 moles of my HNO3 solution. And moles of HNO3 cancel, and you'll get your answer in liters here, right? So this one, doing this route, we just said, look, I notice that this is going to donate 2 hydroxides to the solution, so I'm just going to fix that in here early. And then remember that 1 hydroxide is going to react with 1 hydrogen. Whereas here, I just remember when I do my multimole ratio between base and acid that it's a 2-to-1. But either way, you should get the same answer. Let me plug this in. I've got 0.012 multiplied by 0.015 times 2 divided by 0.085, and I get the same answer. Does that make sense, Erica? Kinda, yeah. So long as you are taking into account the fact that either 1 barium hydroxide gives you 2 hydroxides, or that 1 barium hydroxide reacts with 2 HNO3s, one or the other. In this, when I did this route, I singled out the OH. But the first thing that I was going to do, I don't know if you remember it, is I said, I'm just going to get rid of all of this and just put this here, right? And that's what this is, okay? So this route gives you that guy, whereas this route gives you this equation. Does that make a little more sense? All right, that's it for this lecture. I'll see you on our next lecture with acid-base buffers.